This is Algebra 2 with Trig, working on Unit 2A.1. Here we're going to be classifying and evaluating polynomials. Here we have a polynomial function. Looks a little bit intimidating, but the main thing to notice are with your variables that you start out for standard form with your largest exponent first, and then you go in decreasing order. The ... just represents that there can be multiple values in between. Things that we know about a polynomial function are the exponents have to be whole numbers. They have to be counting numbers. So no fractions for the exponents on a variable, and no decimals. So we're looking for whole numbers which are positive counting numbers. Okay, the coefficients are all real numbers. So no imaginary numbers. And the one imaginary numbers that we really learned about were the negatives inside of a square root. Alright, if you have 0 as a degree, that means your exponent is a 0. So y equals x to the 0 power. That is going to be a constant. If you have y equals x to the first power, that's going to be linear, a linear equation. Of course, we've done this recently, y equals x squared. Quadratic. And what we're really learning about here are cubics and even to the 4th power quartic. So we'll come down here and discuss if these are polynomials. So I'm looking at 6x to the half power. Well, we talked about how the exponents had to be whole numbers. This is an exponent on your variable that is not a whole number. That's actually means a square root. So no, you can't have that. Not a polynomial. Here we have x to the 5th, and it doesn't go to 4 and 3, but it is decreasing. There's my 4, so it's not in standard form. You do have your square root number here. With the square root as your constant number, it would have x to the 0 power with it. We're still going to consider that a coefficient of x to the 0 power, so not a polynomial. Here we have x to the 3rd power, x to the 2nd power. It doesn't show just x to the 1st power. That's fine. It doesn't have to have every term. X to the 0 power. It does have a fraction, but that is a coefficient. So yes, it is a polynomial. And the type that it is, because 3 is your largest exponent, it is a cubic function. Here we have a negative as our leading coefficient, and that's fine. X to the 4th, that's fine. Oh, x to the negative 2. You can't have an exponent be a negative number, because that actually means put it into the denominator, so you have an x in the denominator. We don't have that as an example. So, not a polynomial. So you're not a polynomial if you have a negative exponent. You're not a polynomial if you have a radical. And you're not a polynomial if you have a fractional exponent. A fractional exponent means that you're taking the square root of the x. A negative exponent means that that x value is in the denominator. We'll talk more about that in the future. Direct substitution. You've been doing direct substitution for years. This is where we like to say f of 2 because we're going to plug 2 in for x, and we do that for every term that has the x. Typically, this has got lots of calculations. We do not call this negative 6. We call that negative 3 times 8 plus 4 minus 24 minus 5. F of 2. When I plug 2 into all my x's, I get negative 24. This would be negative, that would be negative 20, negative 25. So I see that f of 2 is going to be negative 49. So you notice that that took several lines for us to come up with the calculation. Well, synthetic substitution is a little quick format way for us to calculate out what this value could be. So here we're using the same exact negative 3 x cubed plus x squared minus 12x minus 5. So we're still going to evaluate it when x is 2. So when x is 2, we're going to plug 2 in, and we use this bar to help us organize out our exponents, or our, coefficients. So that's negative 3, that's our largest exponent with its coefficient. And then 1 would be the coefficient, and negative 12, and negative 5. Because this is a cubic equation, you're going to have 4 terms. The 3, the 2, the 1, and the no exponent, no x value term. You always drop down. Alright, when we're doing synthetic substitution, you drop down your negative 3. From here, you're going to multiply and bring it up here. Negative 6, add those together. Then you multiply to get negative 10, and you bring it right here. So that's negative 22. Then you multiply, that's negative 44, and then you add, and look what happens. We've got negative 49, the same thing that we calculated here. So f of 2 is going to equal negative 49. So that's kind of a shortcut method for us to substitute in a number. It's called synthetic substitution. So we can practice this a few more times. We're going to take our 4. Our x cubed is the largest exponent, so it has a 1 in front of it. And then a negative 5, then a 6, then a 1. You always drop that down, multiply, and add them together. Multiply, add them together, multiply, and add them together. So f of 4 equals 9. So for this polynomial, which is specifically called a cubic, it has a point where x is 4, y is 9. So here we're going to plug in a negative 2. X to the 4th x to the second, or x to the fourth, x cubed has a 2, x to the second has a 3, but notice it doesn't have x to the first. So we have to hold that place value with a 0. And then negative 7. So x to the fourth has to have 5 terms, where x to the third has 4 terms. We bring down our 1 and multiply, add them together, multiply, add them together, multiply, add them together, multiply, add them together. So our f of negative 2 is going to equal 5. So that means for this quartic polynomial, when you plug in negative 2, or on the graph where x is negative 2, the y value would be 5. On the flip side, the end behavior of a function's graph is the direction the graph goes. And we're talking about that for when x is positive and when x is negative. So what we're going to do, we're going to look at the degree. Remember, when the degree is 1, it's linear. When the degree is 2, it's quadratic, and so forth. We're going to look at a degree that is odd. And the leading coefficient is positive. We're not looking at specific cases, not necessarily when it's 1 or 3, but the pattern, whenever it's odd, we know that they're going to go in opposite directions. And when the leading coefficient, the number out in front, is positive, you know that it's going to be increasing to the right. So if the leading coefficient is positive, as x gets bigger, and you're cubing a big number, the leading coefficient doesn't change it. It's just positive. It keeps it large. The odd degree makes it go in opposite directions. So if it was odd, it might swing through here many times. If it was odd, it might be just a straight line, if it was linear. But it's still odd. It still goes in one direction and the opposite direction. So as x approaches positive infinity, the function is increasing. So that's going to positive infinity. As x approaches negative infinity, as you look to the left, the function goes to negative infinity. It's going down. Let's look at when you have an even degree. You have an even degree, but a negative leading coefficient. If you have a negative leading coefficient, you're going to be falling to the right, no matter what. You're going to be falling to the right. If it's negative, you're falling to the right. If it's negative, you're going to be falling to the right. If it's positive, you're going to be increasing to the right. All right? Now, if it's even, the even that you're familiar with is a quadratic. When you draw a parabola, they go up, but then they both go down in the same direction because it's an even term. The degree is even, then it's also going to be going down. If it's even, they're going to be going in the same direction. If the leading coefficient is negative, they will both be going down. So if it's just 2, then you would expect it to be something like that. If it was 4, you might see it make more like an M shape. But as x approaches positive infinity, the graph is going down. Every time you have an even degree and a negative leading coefficient, the graph will be going down as you look for x's to be bigger. The graph will also be going down when you look at x's that are smaller. So when you have an even degree, they will be going in the same direction. So we've talked about an odd degree with a leading coefficient that's positive. We've talked about an even degree with a leading coefficient that's negative. Now we can look at an even degree. Even tells us they're going to be going in the same direction. Positive tells us it's going to be increasing to the right. So we know that the end behaviors should be, as x gets bigger, the function should be going up. And if it's an even, like x to the second power, x to the fourth power, x to the sixth power, when x is smaller, when x moves to the left, it's going to multiply an even amount of times, x squared, even amount of times. You're also going to go in a positive direction. So if you want to say that this is a parabola, or if it's to the fourth power, it might make a W type shape. Now the one that we haven't talked about is an odd degree that is negative. Odd degree that's negative. The odd tells you it goes in opposite directions. Odd is opposite, even is the same direction. If it's negative, it's falling. If it's positive, it's increasing to the right. So we know this is going to fall to the right because the leading coefficient is negative. It's odd, so they have to go in opposite directions. So as x gets bigger, you see the graph is going down. We call that y approaches negative infinity. As x approaches negative infinity, as we look to the left, when x gets smaller, the y values get bigger. Goes up as you move to the left. So let's take a look at what we see here. We see a degree 4, 3, 2, 1, and 0. So a degree that is even. Okay, the degree is even. So we know that they're going to be going in the same direction. A leading coefficient that is negative. So if we have a degree that's even and a leading coefficient that's negative, then we know that they're going to both be going down. The negative makes it go down. The even tells them that they're going in the same direction. So what we would say here, as x approaches positive infinity, the function, often we say f of x, I guess that would be better in this case because it's f of x here. F of x approaches, let's see, if it's even the same direction, If it's negative, it's going down. And as x approaches negative infinity, the function will also be going down, because an even degree tells you you're going in the same direction, and the leading coefficient tells you that you'll be going down as you move to the right. Let's take a look at this one. This is a cubic, so the degree is odd. Okay, that means they're going to be going in opposite directions. And the leading coefficient is positive. That means it's going to be increasing to the right. Positive means increasing to the right. Odd means they'll be going in opposite directions. So as x approaches positive infinity, the function, we'll call this one g of x by looking right here. So g of x approaches, x is big, x is to the right, the function goes up. As x gets smaller, when x is small, moving to the left, the function is going down. Let's take a look at this one. This one has a leading, the largest degree is 4. So the degree is even. That's really the only thing we care about. We could call that a quartic. And the leading coefficient, the number in front of x to the 4th, is a positive. So thinking about our graph, if it's even, that's going in the same direction. If it's positive, you know it has to be increasing to the right. So if it's going in the same direction, it has to be increasing going to the left. So when we say x approaches positive infinity, we're talking about what happens when the graph goes to the right. The function, this one is called h, it goes up. And when x approaches negative infinity, otherwise known as the left, the function is also going up. Because that's what happens when you have a positive leading coefficient and an even degree. This one here, 5, 3, 1. Alright, so they're not representing every exponent, but they don't have to. So the degree is odd. If it's odd, you know it's going to go in opposite directions. The leading coefficient is negative, because x to the 5th has a negative in front of it. It's called the leading coefficient. So as x approaches, it's okay to even start with negative infinity. As you look to the left, let's do a little quick sketch. First, we like to look at the leading coefficient. It's negative. That means it's falling to the right. The odd degree tells us that it's going to go in opposite directions. So we look here, when we have x approaching negative infinity, that's moving to the left. We know that our function, looks like this one is called k of x, it's going to approach positive. It's going upwards when we move to the left. Positive infinity. And as x approaches positive infinity, as we move to the right, the graph is starting to fall to negative infinity. When your degree is odd, they will be going in opposite directions. Degree is odd, they will be going in opposite directions. Okay, here we are. Last couple. Describe the degree and the leading coefficient. Well, notice that we're going this way and we're going this way. So we're going in opposite directions. If we go in opposite directions, we know that the degree has to be, what do you think? When it's odd, it goes in opposite directions. Here they're going in the same direction. They're both going down. So the degree for this one has to be even. Here they're going in opposite directions at the end, called the end behavior. What happens towards the ends of the graph. The middle doesn't matter. It goes up, it goes down, it goes wiggly here in the middle. That part doesn't matter. It's the ends of the behavior. The degree is odd. You know it's going to have a 3 or a 5 or a 7 if it's going to have that type of pattern. Okay, then talking about our leading coefficient, see how it increases to the right? So we know that this must be a positive. You see how this leading coefficient would make it go downwards? So it must be a negative leading coefficient. This graph is falling to the right. So when you're falling to the right, you get a negative leading coefficient.